Okay, so as I said, the last few lectures have focused on introducing us to a new type of reaction, that is the pericyclic reactions. And so tonight's problem-solving session is going to revolve around reintroducing the pericyclic reactions to us, as well as discussing the different things that goes with each of the different pericyclic reactions, and doing some problem solving, specifically problem solving around the Diels-Alder reaction, which is perhaps the most useful and complex of the pericyclic reactions. Some reminders for the course. PSET 5 is due on April 23rd by 12 p.m. To B courses. We're going to have a bonus review session on April 27th from 5 to 7 PST. Note this time. And midterm 3 is on April 30th. We don't have the details for how exactly we're going to administer midterm 3 yet. This is still something we're talking about. But the details for that will be given shortly. So with all that, let's get into this. I think pericyclic reactions to me are some of the coolest reactions in organic chemistry. I think when I was learning this class, these are reactions I really glommed onto as like they're evocative reactions that are kind of fun arrow pushing mechanisms. And so the first class of pericyclic reactions that we talked about in class were cycloaddition reactions. And so cycloaddition reactions are the combination of two independent pi systems. This means that they're not conjugated, and they react to form sigma bonds. And so the prototypical reaction in cycloaddition is the Diels-Alder reaction shown here, where we react a diene with a dienophile to make a six-membered ring adduct. And so the arrow pushing for that looks like this. So we can imagine a forming bond between these two positions. And the arrow pushing goes as follows: push, push, push. And we see in this way, we can make this six-membered ring. Now, cycloaddition reactions, as well as all pericyclic reactions, are reversible. For the most part, depending on their nature, will describe the amount of reversibility of that reaction. And most of these reactions can be done under thermal control. Now, for the naming of cycloadditions, we have a pretty simple convention. And has to do with the number of pi electrons in a system. And so we'll note in this diene here, for the case of the Diels-Alder, that there are 4 pi electrons, right? 2 alkenes with 2 pi electrons in them each. So that's a 4 pi system. And in the dienophile, we have 2 pi electrons in just the one alkene. So there's 2 pi electrons here. And so the naming convention is as follows. It's just 4 plus 2 with brackets. So it's the number of pi electrons in one plus the number of pi electrons in another. And this is quite useful because it describes, in this case, the six-membered ring that we're creating. And so we'll note that in this system, we've created or moved 4 pi electrons to 4 sigma electrons and 2 pi electrons. So this is the very simple naming convention for the Diels-Alder reaction, and it describes and can be used to describe a variety of different cycloaddition reactions. We'll do some practice with how to identify and name cycloaddition reactions later. And we'll really dig into not only the stereochemical outcomes, but also the thermodynamics of the Diels-Alder reaction later today. A subsection of the cycloaddition reaction is the chelotropic reaction. Chelotropic reactions, there's multiple. And this is just any cycloaddition reaction where one of the partners is just a single atom. So here's a classic example where a diene can be reacted with sulfur dioxide, which in this case is and the electron pushing looks like as follows. To generate this 5-membered ring adduct, and in this case, it's simply just like a cycloaddition reaction, except the dienophile unit in this case is a single atom, so it's just sulfur. And so chelotropic reactions are a subset of cycloaddition reactions. Does anyone have any question on cycloaddition reactions writ large? We'll do some more practicing and dig in deep on them later. Okay. Then no questions. We'll move on to the second type of paracyclic reactions that we covered, which were electrocyclizations. And so the big difference between cycloadditions and electrocyclizations is that electrocyclizations are concerned with a single pi system. And so that means a single conjugated pi system reacts to form sigma bonds. And so here is a good example where this tetraene can react to form this cyclooctatriene. And so you could envision the flow of electrons looking like this, where we form a sigma bond and shift all of our alkenes around in a concerted fashion to generate this product shown here. And you can also imagine the reverse reaction, wherein we push electrons to break the sigma bond and move the alkenes around in concerted fashion. And this is how you can interconvert these two. And these reactions are named quite simply for the number of pi electrons in the cyclization reaction. And so we see in this tetraene that there are 8 pi electrons, and that makes 6 pi electrons and 2 sigma electrons. And we'll call this an 8 pi, in this case, 8 pi electrocyclization. And the reverse is, you can describe it as an 8 pi retro electrocyclization, or a retro 8 pi electrocyclization, or an 8 pi electrocyclic ring opening. Any of those are acceptable terms. And so it's simply named for the number of pi electrons in the reaction. Here is an interesting example of the 4 pi electrocyclization. And we'll note for the 4 pi electrocyclization, we can imagine the arrows moving like this to generate a product. And the cyclobutene can also open in a retro 4 pi electrocyclization fashion to give us back this butadiene precursor. Now, what I think is particularly telling about these reactions is that they are oftentimes controlled or thermodynamically by the substrates themselves. And so in the case of the 8 pi electrocyclization, we'll note that we are forming a sigma bond at the expense of net 1 pi bond, right? We go from 8 pi electrons to 6 pi electrons and 2 sigma electrons. And we know that sigma bonds are stronger than pi bonds. And so with that in mind, we would conceive that this equilibrium would lie somewhere to the right, because we're forming a stronger bond than we're breaking. But in strain systems, like this cyclobutene, where we're forming a strain system, that imparts a degree of strain relief upon the retro reaction. And so in this case, the reaction will lie to the left. And that's simply due to, and if we look at this as a thermodynamic picture, it's simply due to the strain imparted on the 4-membered ring system. And so electrocyclization reactions tend to give more stable products, with the exception of cases where you're making, or where the starting material is strained, or there's some sort of strain relief process. But that's a really useful way for us to use cyclobutenes, is that they can then open up and do chemistry. And so this has been exploited in lots of really cool and creative ways. Is there any questions on the electrocyclization reaction? Okay, moving forward. The third type of pericyclic reaction that we discussed in class is the sigmatropic rearrangement. And this is can be simply described as a sigma bond traveling across a pi system. So in this classic sigmatropic rearrangement shown here, we see that essentially traversing this transition state shown here, we can interconvert between these two non-conjugated dienes. And so we're, in this case, breaking this bond and forming this bond. We can do that with arrow pushing like this. Oops. And of course, the reverse reaction would look like this. And this way we can interconvert between these two. The sigmatropic rearrangement is another interesting one where in this picture here, it makes the same starting material and product in this equilibrium, but using a variety of strategies, we could perturb this equilibrium and do useful chemistry with it. And a great example of this is the oxycope reaction. So this is and we'll do the naming convention here as well. So this is a 3,3 sigmatropic rearrangement. And so the naming convention here, I think, is a little trickier than the others, so it's worth spending a second to talk about it. Is essentially what you think about is we think about in the sigmatropic rearrangement, a group migrating across a pi system, right? And so in this way, we name it based on what the group is and how far it travels. So in this case, we can see, especially in the transition state here, what we have is a group, this allo group, which is 3 carbons big. So the group has 3 components to it. So that's the first 3. So the first letter, the first number describes what size the group is in terms of how many atoms it is, or how many positions it is, and how far it travels is the second number. And so we see that this carbon-carbon, the electrons from this bond travel 1, 2, travel 1, 2, 3 positions, right? So this allo group migrates 3 positions, so it's a 3,3 sigmatropic rearrangement, where the first number is number of atoms meaning carbons or oxygens or whatever the migrating group is, and the second is how far it travels. And we'll do some practice on the naming conventions of the sigmatropic rearrangement in a little bit. So an example of how we can use we can gain some thermodynamic control over the sigmatropic rearrangement, because we do recognize that in this case, we're breaking a carbon-carbon bond and forming a carbon-carbon bond. This is a thermoneutral reaction. We can perturb it in a couple of interesting ways. One of which, as I said earlier, is the oxycope reaction. So all this requires is the substituting of our non-conjugated diene with a hydroxy group. And now if we envision doing the 3,3 sigmatropic rearrangement, we can push arrows like this. We can get a reversible sigmatropic rearrangement. Oops. Followed by what is an effectively, or is not necessarily effectively reversible, but another reversible equilibrium, which is tautomerization, right? Where we formed an enol here, and we know that enols are readily tautomerized to the corresponding aldehyde, right? We talked about this earlier this semester, in aldol chemistry. And so in this way, there is a relatively thermoneutral equilibrium followed by a more thermodynamically favored tautomerization process, and it drives the whole process to the right. And so in this way, we can gain some amount of thermodynamic control over the sigmatropic rearrangement by tying it off to downstream thermodynamically favored processes. So I think this is a really great example. This is the oxy-cope reaction. And really shows one of the potential utilities of the sigmatropic rearrangement, and has been used time and time again in synthesis. Any questions on the sigmatropic rearrangement? How do we know when pericyclic reactions will occur in the first place? That's a great question. I think it has to do mostly with recognizing the different types. And just knowing that it's possible for them to occur, right? So when I see this sort of non-conjugated pi system, I can think, oh, a sigmatropic rearrangement might be possible. If I see two pi systems that could come together, I think there has to be a cycloaddition, or there could be a cycloaddition. I think since pericyclic reactions can occur just thermally without the addition of any reagents, a telltale sign is also just reaction occurring without the addition of anything upon just heating. But it's just something that comes to do with being very aware of the different types of pericyclic reactions. And so once you're comfortable with all the different types, you can recognize, oh, that these precursors look like they could do a sigmatropic rearrangement. This could do a 4-pi electrocyclization or a 4-pi electrocyclic ring opening. It is just about pattern recognition at some level. Great question. Yeah, sorry, you said we need heat to run these reactions, or we don't. In many cases, they require heating. In some cases, they don't. For example, the oxy-cope reaction is fairly favorable and can proceed readily at room temperature, or some Diels-Alder's reactions will happen at room temperature. But notably for these types of reactions, you tend not to have to add any other reagent. Some of them will require heating depending on the barrier for the transformation, and some of them will proceed at room temperature. It really depends on the substrates. But the point there is that many of these reactions can occur just thermally. We talked about in class also that some types of cycloaddition reactions might require photochemical activation. And so we can talk about that too a little bit later. Okay. And the last type of pericyclic reactions, the one that I think is oftentimes a little maybe remembered, is the group transfer reactions. And these are essentially, can be thought of as sigma bonds migrating across pi systems, but in a separate, but they're separated or become separated. And so it's essentially sigmatropic rearrangements, but the two units are disparate. And so the classic example of this is the Ene reaction shown here, wherein an allyl group can be added across an alkene in a fashion that looks like this if we were pushing arrows. Right, so there's a nice little 6-membered transition state here that can form this bond. And so the Ene reactions or group transfer reactions are always one to look out for. And you can think of them as sigmatropic rearrangements that bring two pieces together or take two pieces apart, right? Because these reactions also are always have the potential to be reversible, depending on what the reaction is. And to make that really clear, the next slide is it has quite a few practice problems, maybe too many. I may have gone a little overboard with the number of reactions on the next slide. So we're going to spend maybe the next 15, 20 minutes working on some practice problems. And what I want you to do with these problems is to recognize the type of pericyclic reaction that's occurring, right? So for example, if it's a cycloaddition, write cycloaddition. I also want you to draw the arrows for the transformation. I also want you to, for cycloaddition, sigmatropic rearrangements, or essentially for all of them that aren't group transfer reactions, I'd like for you to use or write down the naming convention for those pericyclic reactions. So we want to draw arrows, draw arrows, name the reaction, and also give the M plus M type name. And so let's take some time to do this. We'll say around 15 to 20 minutes. Okay. And if you finish early or whatever, just put a yes. Put a yes in the participants window if you finish, or if you get stuck, or you just want to move on, and we'll go from there. Okay, so we'll take some time to do this starting Okay, so let's take some time to go over these. I think we've had a good amount of time to get through at least some of them, and hopefully you've got a chance to look at each of these, and we'll go through one by one and kind of talk about each of them, because we do have to move on to the rest of the stuff we have planned today. Okay, so this first one, does anyone have any suggestions on what it is? You can type your answer in the chat if you'd like. Just for the name, I can draw the arrows, of course. Does anyone recognize from what named reaction this step is from? Yeah, it's a group transfer reaction, and the arrows would look something like this. And we should be familiar with this from the Swern reaction, the Swern oxidation reaction. And so this is a group transfer reaction, and it's arrow pushing we're actually already familiar with. We just didn't put a name to it at the time. So this is a group transfer reaction, and it is the oxidation step from the Swern reaction. And so this is a reverse group transfer reaction, right? So we thought about group transfer reactions and bringing two things together, but we also have to recognize we can use group transfer reactions to bring two things apart. And so intramolecular eliminations, like we did in the Swern oxidation and the Jones oxidation, are examples of retro group transfer reactions. What about the second one in the top middle here? Yeah, and someone just sent me a message to clarify the difference between a sigmatropic rearrangement and a group transfer reaction is that a group transfer is a sigmatropic rearrangement that involves 2+ molecules. I'll say that's mostly correct. The important thing here, yeah, we'll say that's correct. The group transfer reaction involves bringing two parts together, or a part where a sigmatropic rearrangement is the rearrangement of sigma bonds across a pi system. So they must be linked. So for the second reaction, someone, you can, some of you have set it up to message me privately, but you can also send these messages to everyone. It's an open forum where we can all discuss. And someone quite correctly pointed out the second reaction is a cycloaddition reaction. And so I can draw arrows just like this. To give this product. So this can be named in actually a couple of different ways. We talked about this type of cycloaddition reaction at the end of last class. So specifically, this is a dipolar cycloaddition. And so this molecule here, this azide, is a 1,3 dipole. And so dipolar cycloaddition reactions can be classified and can be named several ways. If we just use basic cycloaddition nomenclature, we'll note that there's 2 electrons from the alkyne participating in the cycloaddition reaction, plus 2 electrons from this from the lone pair of the azide, as well as 2 electrons in this alkene, or this nitrogen double bond. So this is a 4 + 2 dipolar cycloaddition. Right, and you can recognize here that we're bringing together 2 pi systems to exchange pi bonds for a sigma bond. Also, another name that you might see in the literature for this is a 3 + 2 dipolar cycloaddition. Notably, if you see this in the literature, it should use parentheses instead of brackets. This is a special naming for cycloadditions that names them based on the number of atoms. And I don't put this here to confuse you. I put this here just in case you see it in the literature as you become chemists. And we should know that this is distinct from the common and accepted naming for cycloadditions, where the brackets indicate the number of electrons, the parentheses indicate the number of atoms. And so that's something you might also see, but this is a 4+2 dipolar cycloaddition. For the purposes of this class, we're going to use this bracket notation that indicates number of electrons involved. Okay, what about this one here? Top right. Okay, so this one is a sigmatropic rearrangement, and I'll draw the arrows for it that look like this. So we can see that this hydrogen can migrate to this position. So if I star it, we'll note that we're taking a hydrogen from this position and moving it to this position. We can push electrons like this. And so in this way, we move this hydrogen across the pi system. Okay, and so this is the shifting of a sigma bond across a pi system. And so it's a sigmatropic rearrangement. If we're going to number it, well, remember our naming convention here is the number of atoms that are migrating followed by the number of atoms it travels. So in this case, we have one hydrogen that's migrating. So this is a 1. And it is migrating across 1, 2, 3, 4, 5 positions. And so this is a 1,5 sigmatropic rearrangement. Any questions on that? Okay, so for this next one, I think there's 2 possible answers here. For the mechanism, could you draw the arrows counterclockwise instead? Yes. So for this next one, there's 2 possible answers, and I'll accept both, because there's 2 steps here, actually, or maybe 1 step, depending on how you did it. And so does anyone have some answers for this? Does the H0 migrate across 1 atom? That's a good question. So in essence, you could the question there is why is it 5? And you could, yeah, I guess the point there is just you're counting the maximum pi system because it has to, because of the way we're pushing the electrons here, it involves all 5 of those atoms. I'm just thinking if there's another way you could draw it to give the same, to give a similar, the same outcome. And I don't think there is. And so since we're involving, you're right that the hydrogen atom seems to be moving just 1 position, but the movement of the electrons is across the 5 atoms of the pi system. So it's a 1,5 shift. Good questions. So what about this one? Yeah, sigmatropic rearrangement. I think that's a valid answer here. And so the arrows for the sigmatropic rearrangement would look like this, right? This is the allo group moving across a pi system. This is accelerated by strain relief. And so the arrows would look like this, and this could be a 3, 3 sigmatropic rearrangement. It's 3, 3 because what is migrating here is an allo group, and it's traveling across another allo group. So 3, 3 sigmatropic rearrangement. Alternatively, I think there's another possible answer here, which starts with a 4 pi retro electrocyclization, as someone just mentioned in the chat, that I think is also possible. So you can do a retro 4 pi electrocyclization that would get you to get you to something that looked like this. Oh my goodness. It's very hard to draw 8-membered rings, apparently, or close to 8-membered rings with PowerPoint highlighter. Okay. It would get you to a product that looked like this. And this could do an 8 pi electrocyclic ring closure. Arrows that look like that to get you to your product. So this could be a 4 pi electrocyclic ring opening, followed by an 8 pi electrocyclic ring closure. And at this point in the class, we have no good way of picking one of these mechanisms versus the other. We'll learn later on that the stereochemistry of this cyclobutene would be important to deciding which of these two could proceed. But we have not learned that yet, so it could certainly be either. Yeah, so 4 pi electrocyclic ring opening. And then an 8 pi closure. Okay, what about this next one in the middle? Yeah, so the question in the chat is, when we do the reverse mechanism, we still consider the original number of electrons in the pi system. Yeah, so we name it based on the forward reaction, essentially. And so the reverse is the reverse, but we name it based on the forward. And then this next one is indeed a sigmatropic rearrangement. Does anyone have the numbering for it? Two, 3, correct. And so in this case, we see that our group that is migrating is 2, and it's migrating across 3 atoms. And so it is a 2,3 sigmatropic rearrangement. Okay, and what about the next one? Yeah, someone says group transfer reaction, and I think that's correct. I'm going to redraw the oxygen down here for the arrow pushing. And so that looks like this. To give this peroxide product. And so this is a group transfer reaction. This is the example of a forward group transfer reaction. So we take two parts and we bring them together. This is a group transfer. Okay, what about this next one? Okay, so one answer for electrocyclization, and we'll see that's actually not quite the case. So the electron pushing would look something like this, where you would have 3 molecules of the alkyne, and we can push electrons in this fashion. And now, since these are 3 distinct pi systems, we'll call this is a 2 plus 2 plus 2 cycloaddition. Now, it turns out that to do this reaction just thermally is very difficult due to the high entropic barrier of bringing 3 molecules together at once. But it's kind of like a holy grail reaction that people thought you could do for a long time, and so it's possible to do with catalysis. But the point is, it's a 2 plus 2 plus 2 cycloaddition reaction. And so while cycloaddition reactions with more than 2 components are rare, they are possible. And so this is an example of one. Is there a difference between drawing the arrow into empty space or drawing it to an atom? Not really. I prefer to do it so as to envision the bond that is forming, which is why I kind of draw it to empty space. Some people will draw it just from carbon to carbon. I learned it the one way. Some people prefer it the other. Doesn't matter to me. It just is, when I'm doing it, it's to represent the fact that there is a bond being formed there that we're dumping electrons into. Okay, what about for this last one? This is a type of decarboxylation, but let's name it based on, the nomenclature we've talked about here. It's a retrocycloaddition. And so we can push the arrows as follows. So let's bring these up here. Here. It's making carbon-oxygen double bond. pushing down to make a carbon-carbon double bond, and pushing this way to form a carbon-carbon double bond. And so this is a 4+2 retro cycloaddition, or a retro 4+2 cycloaddition. And you could see the forward reaction would look something like this. Right, looks just like a Diels-Alder would. And so that's a 4+2 cycloaddition if we went this way. And so if we go the other way, it's a retro 4+2 cycloaddition. And so we also have to remember always that cycloaddition reactions can be reversible as well. And so this is a retro cycloaddition. Any question on these? There's such a thing as a retro group transfer, or the forward group transfer can be. Yeah, so an example I would say is shown here. So I would say that even though we tend to just call them group transfers, we can call this a retro group transfer here, right? Where we take one piece and make it two pieces. And so this intramolecular elimination from the Swern oxidation is a retro group transfer reaction, whereas this oxidation reaction here is a group transfer reaction, so it's the forward. So group transfer reactions can have forward and reverse as well, the forward being taking two pieces and putting them together, the retro being taking one piece and fragmenting it into two. And so that can be the convention for that. Okay, any more questions on this? Okay, so I think that that was some good practice on recognizing the different types of pericyclic reactions. I think it's crucial to understanding a lot of the synthesis problems as we're going to do, as well as box problems, just being able to be very clear and quick on picking out these different reactions. So I think it's important to practice these. I think also on the problem set, there's a big problem that is just essentially doing this. So by the end of all that, we should be quite good at this. So we'll move on to looking more deeply at the Diels-Alder reaction. We talked about the Diels-Alder reaction yesterday in class, as well as cycloadditions more specifically. And this is the cycloaddition reaction that I think organic chemists are really most familiar with, and is used probably more than any of the others. It turns out that, you know, for years and years now, it's one of the most powerful ways to make carbon-carbon bonds, and do it in ways with predictable stereochemical outcomes. And that's really been to the great benefit of the chemistry community. And so the Diels-Alder is a historically very important reaction, and is still synthetically quite useful. And so one of the important factors in the Diels-Alder reaction is the profound effects of substituents upon its reactivity. And so now we're going to talk about substituent effects and do some practicing, so we make sure we're very quick and then we can understand how substituents affect the outcomes of Diels-Alder reactions. And so classically, the Diels-Alder reaction takes place between a diene and a dienophile. But these tend not to be particularly electronically matched for this reaction to happen readily. So we talked about this in class, that while this reaction can proceed, the barrier to do so can be quite high and can require harsh conditions like high heating and long temperature, and high heating and long times. And so the practical way around this is to add substituents onto your diene and dienophile that electronically match them. And so let's talk about why that's the case. And so if we look at the molecular orbitals that I've shown here, we can say for a 4-pi system like the diene, we can fill in our 4 electrons. And so this orbital here is the HOMO, and this here is the, and this here is the LUMO. For our dienophile, we just have a 2-electron system, and so this is the HOMO, and this is the LUMO. And so for efficient reactivity, we need mixing of the frontier molecular orbitals, and so it's either going to be a reaction of the HOMO of the dienophile with the LUMO of the diene, or the HOMO of the diene with the LUMO of the dienophile. And the amount of overlap, or the difference in energy between those two levels, is going to describe electronically the barrier to this reaction. And so big HOMO-LUMO gaps means less reactivity. And so as we bring the HOMO and LUMO gap smaller and smaller and these energy levels closer together, we're going to see faster reactions. And so this is fortunately something we control with substituent effects. And so classically, the way you do this is a recognition that electron donating groups raise the energy of all orbitals, and electron withdrawing groups lower the energy of all orbitals. And so you can see in this way, we can start to do electronic matching. And so a potential solution to sluggish reactivity here could be for our diene to raise the energy of the HOMO, so it's now closer in energy to the LUMO, right? And so we could do this by adding electron donating groups to the diene. Now, another way you can think about doing this is also, for example, if we're looking at this HOMO-LUMO overlap, is to lower the energy of the LUMO of the dienophile. So if we lower the energy of the LUMO by appending electron withdrawing groups, we now see that these are better electronically matched, and the HOMO-LUMO gap is much smaller, and so that should have better reactivity. And you can also think about doing this the other way around. So you could raise, by putting electron donating groups on the dienophile, you could raise the energy of the HOMO, and with electron withdrawing groups on the diene, you could lower the energy of the diene LUMO. So both these strategies can be used to gain better reactivity, or gain more efficient reactivity. And so we have a convention which is saying if we put electron donating groups on the diene, like in this first example here, and react it with an electron poor dienophile, like this one shown here, right? This is an electron withdrawing group. This is an electron donating group. If we put electron donating groups on the diene and electron withdrawing groups on the dienophile, this is a normal demand Diels-Alder. And if we put electron withdrawing groups on the diene and electron donating groups on the dienophile, this is inverse demand. That's just by convention. I saw a good question in the chat, which is, why do electron donating groups raise the energy and why do electron withdrawing groups lower the energy? This just has to do with the, I guess you can think about it as electronic energy levels. And so the electron withdrawing group pulls electron density toward it. The electrons in those orbitals are therefore stabilized by the inductive effect of that electron withdrawing group or the resonance effects of that. So something, an electronegative atom takes those electrons, that lowers their energy, and so all the energies of these orbitals are lowered by an electron withdrawing group. Similarly, when you put more electron density into something, that raises the energy of those electrons in those orbitals, and so electron donating groups electron donating groups raise the energy of all the orbitals. And so this is also just seen by, if you think about adding electronegative atoms. And so if we like replaced one of the carbons here with oxygen, oxygen's more electronegative, it lowers the energy of all orbitals. If you replaced one of the carbons here with silicon, silicon's more electropositive, it raises the energy of all orbitals. This is just a classic orbital mixing phenomena. And so we have these two different types of Diels-Alder reactions, normal demand and inverse demand. Interestingly, when you run these reactions, you see one regiochemical outcome for both. You could expect, for example, in this normal demand Diels-Alder to see this product as well, but you don't see it. As well as with the inverse demand Diels-Alder. And so let's talk about why that is. This is an electronic matching problem. And so it turns out that the ground states of these orbitals, while we draw the orbital coefficients like this, they are actually have different, these lobes have different sizes depending on the substituents. And so they can interact, and the lobes with highest or correspondingly matching orbital coefficients will overlap. And the other way to think about this is just polarization. And I think that's maybe the easiest way of thinking about it. And so what we'll say is that negative goes to positive. And so this terminus of the diene is the delta negative side, and this of the dienophile is delta positive. And so how did we get there? I think the easiest way to rationalize this is a classic resonance argument where we can dump electrons through the pi system here. And so you could imagine this resonance structure. And so we see in this resonance structure, we put negative charge on this terminus. And similarly, in a resonance structure here, the ester group can accept electron density. And you get positive charge here. And so now that we recognize the polarization in these dipole, or in these the diene and dienophile, we recognize that negative goes to negative, and then the other two sides go together. That's the problem solving I normally do. And so we can do the same thing over here, where we see that in resonance structures, electron density is pulled into the nitro group. And so this is delta positive, and electron density is dumped from the methoxy group into the alkyne. And so this is delta negative. And so delta negative goes to delta positive, and the other two sides go together. And that's how we explain these regiochemical outcomes. Does this make sense? Any questions on this? Okay, so we're going to do another practice problem here on deals all their substituent effects. And we're going to have to do this one kind of quick because we are running up on time. And so let's say like 7 minutes, maybe 6 minutes or 5 minutes. So work on those, and then we'll come back in a few minutes and talk about the answers to this. Okay, let's talk about these. It's okay if you're not done. It's just in the interest of time, we should move forward. The first part here is to label the positive and negative ends of the diene or dienophile. I've kind of gone through every possible position, of all of these, and we should be able to assign what position is negative or the most negative and which position is the most positive. And most of the way I'm doing this is almost always through a resonance picture or some kind of electron donation through induction picture. In this first example, we'll see that if we draw or push electrons from lone pair of the methoxy group, the electron density ends up on this terminus of the diene. And so we'll note that because of the position of the methoxy group, it cannot donate this way. And so this is the negative end of the diene. And so this will be matched with the positive end of the dienophile. In this picture, we see that our electron donating group, which is this terp-butyl group, while it can't donate through resonance, it does have it can donate electrons inductively. So it can give electron density to the diene. And so you can think about it pushing electrons this way. And in doing so, we can recognize that carbocations next to this terp-butyl group are going to be stabilized most effectively. And so we can kind of push electrons like this to give a resonance form that looks like this. Now this is the most stabilized resonance form because the positive charge is next to our electron donating terp-butyl group. And so the delta negative side is also this position of the diene. And so we can do similar things for electron poor dienes. In this case, electrons can be accepted into the ester. And so this makes this the partial positive end of the diene. You can also do the same with nitriles. I'm sorry, I meant to put this on this position. You can pull electrons into the nitrile just the same way, but if it's on this position, we see that it can only go from this alkene. It's not in conjugation with this alkene. And so this is the delta positive end. For dienophiles, when you have an electron withdrawing group, like a nitro group, they can also accept electrons. So this is delta positive. And when you have electron donating groups like amines, they can donate electrons. So this is delta negative. And so I think a resonance picture works really well for determining the most electron rich and electron poor positions of our dienes and dienophiles, and that's how we can match them in Diels-Alder reactions. Does this part make sense to everyone? Excellent. Next is how fast these things will react in Diels-Alder reaction with A. And so A here is a very electron poor dienophile. And we know it's very electron poor because it has 2 electron withdrawing groups on it. And so there's a couple of things that we'll be looking at here in terms of its reactivity. We know since we have an electron poor dienophile, we're looking for electron rich dienes. And so the most electron rich dienes will react fastest. And from not just an electronic bias, we know that there is a bias toward reactivity for alkenes that are in the S-cis configuration. And so we recognize in order for the Diels-Alder reaction to occur, talked about this in class, that the diene must take the S-cis configuration as opposed to the S-trans configuration, even though the S-trans configuration is more favored thermodynamically. And so one strategy to accelerate Diels-Alder reactivity is to lock the diene into the S-cis configuration. And so those are the major things I'm looking at when I'm determining these factors. And so when I look at all of these, and I'll label them A, B, C, D, and E, which do we think is going to react fastest, A, B, C, D, or E? B, right? So B has 2 electron donating groups, so it should be the most electron rich, so it'll react fastest. Who do we think will react next fastest? A, yeah. So while A, D, and E are all certainly electron rich, locking A into the S-cis configuration is going to increase its reactivity. Now, what we can recognize is that amongst these dienes, this one with the nitro group is quite electron poor because the nitro group is an electron withdrawing group. And so we'll expect this to react the slowest. And so when we compare now D and E, we should draw them in their S-cis configuration. That might give us some amount of insight here. So what we see with D, when drawn in the S-cis configuration, versus E, that there's quite a bit of steric clash here between the methyl groups in D. This disfavors the S-cis configuration and favors the S-trans configuration to relieve that strain. And so it's harder for D to adopt this orientation required for reactivity. So it's going to be slower than E, who can more easily adopt that configuration. And so it'll, so E will be 3 and D will be 4. Any questions on this? Excellent. Okay, so let's move on to the Diels-Alder stereochemistry. And so a classic example of the Diels-Alder reaction is the dimerization of cyclopentadiene. And so the electron pushing for this would look like this. So we're forming these bonds, and it can give 2 diastereomeric outcomes. Notably, there's also 2 enantiomers to both of these, but we're going to focus on diastereoselectivity. So we have 2 diastereomeric outcomes, the exo and the endo products. And so we have to understand what factors might lead to one being favored over the other. And so typically we say that the exo product is lower in energy, and in this case it is because the steric interaction between these 2 groups is smaller than the steric interaction between these 2 groups. And so the exo product is less strained. And so this is thermodynamically favored. But when this reaction occurs, so this is thermodynamically favored, this reaction occurs, we see, especially at low temperatures, formation of the endo product. And so endo product, in this case, is kinetically preferred. And so let's look at the transition states that lead to both of these products, and we can start to see why that is. And so I'll draw the diene here, and below it, we'll draw the dienophile. Almost perfect. And we'll note that we're forming this bond. We're forming this bond. And product from this transition state is the exo product. Right, and we can see that's the case. The hydrogens here end up under. Okay, and so this is the transition that leads to the exo product. We see that much like the exo product itself, the transition state is unstrained, and that's great. But what we'll note is the endo, or the transition state that leads to the endo product, has a bit of extra stabilization that comes from secondary orbital interactions. And so we're thinking about the formation of these bonds still, but this transition state is actually kinetically preferred. And the reason for that is the interaction of these internal orbitals of the diene with these pi orbitals on the dienophile. And so when there is on your dienophile a pi acceptor or pi donor group, it can interact with your diene in a secondary orbital interaction. And this secondary orbital interaction is stabilizing to the transition state. Notably in the product, that interaction is not really there. And so it does not affect the thermodynamics of the product, but it does affect the thermodynamics of the transition state. Right? And so this transition state is lower in energy and therefore leads to the kinetic product. And so this extra stabilization in the transition state leads to the formation of the endo product. Right, and so this is an additional consideration when doing deals all their problems, is we have to look at these possible transition states, both the endo and the exo transition state, and decide based on what the diene and dienophile are, which of these two transition states is lower in energy. And once we know which are lower in energy, we can determine the stereochemical outcome depending on whether or not the endo or exo product is preferred. Does this make sense? We're going to do a couple of stereochemistry practice problems to wrap up the night. Okay, so we can put this to the test in these practice problems. So I'm just going to give you like a very short amount of time to try these practice problems on your own, and then we'll do them as a group. So just take a few minutes, try and especially try and solve the first one, draw the two transition states that you think would lead to corresponding products, and we'll talk about it in just a few minutes, and that's how we'll wrap up the night. Yeah. Okay, so let's, in the interest of time, let's work on these together from this point onward. And so I'll show you the way I do these problems always. I think sometimes, especially in the way Felix taught it yesterday, the part where you take the transition state to the product can be really confusing for the stereochemical outcomes for some people. And so I'm going to show you a more stepwise way of doing it that will hopefully allow you to better see the stereochemical outcome. And so we have this diene and dienophile shown here. We can react them as such. And that will proceed through one of two transition states. Shown here. The first being the exo transition state. And the second being the endo transition state. Now, in this case, we have a dienophile that does not have a good endo donor acceptor, right? There's no pi character to these positions, and so it cannot stabilize the endo transition state through the secondary orbital interaction, right? There's no pi orbitals to overlap. And so in a case like this, where there's no secondary orbital overlap, the only thing to consider is steric considerations. And so when we look at these two transition states, we can see that the exo transition state is less hindered, right? Since there's no secondary orbital overlap, we're only considering this steric clash. This second transition state here is going to be higher in energy than this transition state. And so we'll expect to see exoselectivity. And so what does that stereochemical outcome look like? And so what I do to come up with the stereochemical outcome is I just redraw the transition state. I'm going to draw in the hydrogens explicitly here. I just redraw the transition state with the bonds formed. And that might seem, and you can skip steps if you are quite good at this, but I like to do it this way just to make sure I get everything right. And so I've pulled up this bridge a little bit just for the sake of seeing it. But note here, I'm not really changing the position of anything. I'm just redrawing the transition state with everything drawn in the same way. And now that I've redrawn the transition state as the product with the stereochemical outcomes all shown, I can flatten this out to what the 2D representation of the product is. And so I can see that this bridge, it's on the same face as itself, and it's also on the same face as these methyl groups, right? So the bridge and the methyl groups are on the same side. The hydrogens are on the same side as each other. And so I can take that information and convert it to 2D representation. Okay, so that's like that. Back. Back. And now we have our exo product with all the stereochemistry. Notably also, there is the other enantiomer of this. There is, in these cases, there's no difference in energy between these two enantiomers, and so you will make both because your starting materials are both achiral. And so you also have this enantiomer. Both of these are formed, and that enantiomer comes from the enantiomeric transition state, where instead of approaching from the bottom, this dienophile can approach from the top. And both of those approaches are the same energetically, and so you can get either enantiomer. And so we can do the same type of analysis for this problem. I'm going to now draw my diene in the S-cis configuration. And so to do that, oops. Right. Notably, the methyl group here is out. It's still out here. And so we have our methoxy group here. Could you repeat why we are considering the sterics in this case? Can't the empty pi orbitals of the methyl group interact favorably with the diene? So there's not really empty pi orbitals on those methyl groups, right? They are completely, the methyl groups each have each of the methyl groups has 3 sigma bonds to hydrogens, which don't have proper symmetry or good symmetry to overlap with the pi orbitals, right? So the methyl groups don't have empty pi orbitals; they have 3 sigma bonds, and so there is no pi orbitals there. Are the two products that you drew the same product, or are they enantiomers? Oh, I guess actually you're correct in this case. The product is achiral, right? Yeah, because it has a mirror plane. So actually, in this case, there's only one outcome because the 2 different transition states give products that are achiral or are meso. They're meso. That's a good question. Did I answer your question, Caitlin? Great. And so we have the diene, and very quickly we can see that the electron donation here makes this the delta negative terminus of the diene, and electron acceptance here makes this the delta positive of the dienophile. And so we want this end to react with the delta positive end of dienophile. And so our transition state could look something like this. This would be the exo transition state. We also have the endo transition state. We're in this forms bond here, and this forms bond here. We have that crucial secondary orbital overlap here. And so this endo transition state is favored in this Diels-Alder reaction because of this orbital overlap. And so the product that corresponds to this endo transition state looks like this. We still have these groups that I'll draw explicitly. Oops, just a methyl group. And you can see that the aldehyde is back here. And so when I look at this product, I see that, for example, these 2 hydrogens are on the same face as each other. And so when I draw my product, I draw it so that those 2 hydrogens are on the same face as each other. And so I have methyl, hydrogen, hydrogen. Catherine, do you mean to do like what would be like a 4+4 cycloaddition? She responds to that, we see that this is the diastereoselectivity of that, right? We have these two syn hydrogens that I've pointed out in the transition state. And so that's how we can expect to get the diastereochemical outcome here. And in this case, you would expect to see the enantiomeric product that corresponds to the aldehyde approaching from the top face. And so you get a mixture of these two enantiomers. Does anyone have any questions on this? There's a question about whether or not you could make an 8-membered ring using oxygen here. That would be like the 4+4 cycle addition. That's disfavored for a couple of reasons. The orbital matching is not quite good. It's an anti-aromatic transition state. So that would be unlikely. Yeah, actually, I think that's the best reason is it's an anti-aromatic transition state. So it has 8 electrons. Okay, if there's no questions, that's good. I hope you all have a great week. I'll see you all next week. I hope you had you learned something from this, and this helps out with pericyclic chemistry, which I think is a lot of fun. Have a great night. Okay.